Welcome to the video on additional graphs of functions. So first we'll talk about the absolute value function. So this is where y equals the absolute value of f of x, and it takes all your negative y values and makes them positive. So here we have the equation f of x equals x minus 3, and we'll see what happens if we take the absolute value of f of x. So this is the original equation, and then when we take the absolute value, it'll switch to this blue equation. So if you notice here, the negative parts have switched to become positive. So it takes all of your outputs and switches them from being negative to positive. So the same thing would happen if we did f of x equals x squared minus 3. So this is your original function, and then when we take the absolute value, it's going to take these negative numbers and switch them to becoming positive. So our blue function will be the absolute value of f of x. And you can see here, the negative part switched to positive. So this is our absolute value of x squared minus 3. Then we have the absolute value of x. So this is where we're taking f of the absolute value of x. This makes our x values positive, but they can still be shifted down to negative numbers. And if the only x values are raised to even powers, it won't even change the function at all, because an even power will always get rid of the negative. So here we have f of x equals x minus 3, and we'll see what happens when we do f of the absolute value of x. So we're just taking the absolute value of our x this time. So it'll be our blue function. So you can see here, when y equals negative 3, that's when it swaps to becoming our positive values. And this is because our negative 3 is now outside of the absolute value function. So there's our blue function. So now we can see what happens if we do f of x equals x squared minus 3. This is what our x squared minus 3 looks like, and our f of the absolute value of x is identical to it. And this is because x is going to be squared, so every time it's going to be positive no matter what. So taking the absolute value won't change anything. If we use the cubic function, however, our cubic function looks like this, and if we do the absolute value of x here, our f of the absolute value of x, it's going to take those negative values from where y is lower than negative 3 and do a vertical reflection. So there's your x cubed, and then there's your absolute value of your x cubed. So now we have our reciprocal function, which is y over. So now we have our reciprocal function, which equals 1 over the f of x. It takes 1 divided by all the original outputs of f of x, and it has horizontal and vertical asymptotes because it's 1 divided by our function. So for our y equals 1 over the f of x, here's f of x when it's x minus 3, and our 1 over that would look like this blue function here. So it's pretty different than the original function. What you can notice though is that the original function will split our inverse function down the middle. So you can reflect it across the line x minus 3 because that was our original function. So if we change our original function to be x squared, it will look like this, where our original function is our red function and our 1 over f of x is our blue function. And then we have our x cubed minus 3, and it'll look like that. Then we have our function squared, so y equals our f of x squared, and this squares all the outputs of the original function, making all of your real outputs become positive, and it has the same x-intercepts as the original function. So we'll look at our original function of x minus 3 and see what y equals f of x squared looks like. So for this one, they have the same x-intercept. F of x squared turns it into a quadratic function instead of a linear function. So they look very different from each other, obviously. So now we have x squared. So our f of x is our original function, and it's a quadratic. So our f of x squared is now a polynomial with a degree of 4. So it's an x to the 4th power. And they still have the same x-intercepts. Then finally, we'll look at the cubic function, x cubed minus 3. And they look very different once again, but our x-intercepts are still the same. So next we'll learn about horizontal shifts and dilations. So we have our y equals f of ax plus b, which you can factor the a out on the inside in order to figure out more information about your function. So it becomes f of a of x plus b over a, where a will tell you about your horizontal compression. It'll be a horizontal compression by a factor of 1 over a if the absolute value of a is greater than 1. And it'll be a horizontal stretch by a factor of 1 over a if the absolute value of a is between 0 and 1. Your b value will give you a horizontal translation to the left of b over a units for b over a is greater than 0, and horizontal translation to the right of b over a units for b over a is less than 0 or negative. So here we have a function, f of x equals x minus 3, and we'll figure out what happens for f of ax plus b. So we're going to change our a and b values and see what they do. So right now we have b and a both set at 1. If we change b for our bluish purple function, our b is going to move it parallel to the original function. So if b was 10, for example, it would be here. If b was negative 10, it would be down. And if b was 0, then it would be here. So our a, if we change our a, it's going to rotate it about our y-intercept. So it can spin like this. So we'll look at a squared function, so x squared minus 3. If we change our b, it'll shift it left and right. And if we change our a, it'll also shift it left and right, but it'll also give us horizontal compressions and stretches. So now we'll learn about finding solutions to modulus equations and inequalities. So to do so, you'll move the absolute value portion to one side of the equation and everything else to the other side. You'll then take away the absolute value symbols and create two separate equations or inequalities. You'll set one side of the equation equal to the other side of the equation for the first equation or inequality, and then you'll set one side of the equation equal to negative 1 times the other side of the equation and flip the inequality symbol if it's an inequality. If there's an absolute value symbol on both sides, you'll test each section to see where the solutions are. And you'll always want to double check your answers because you can get a lot of solutions that might not actually be real solutions. So for this first one, we'll have x plus 3 is greater than 2x plus 1, and x plus 3 is less than negative 2x plus 1. So we'll subtract x and 1 from both sides to get that 2 is greater than x. For this other one, we'll have x plus 3 is less than negative 2x minus 1. So we'll add 2x to both sides, and we'll subtract 3. So we get 3x is less than negative 4, so x is less than negative 4/3. We'll draw a number line with our negative 4/3 and 2, and then we'll plug in values to see where the solutions actually exist. So if we plug in something less than negative 4/3, like negative 2, we'd get negative 2 plus 3, which is 1, and the absolute value of that is 1, is greater than 2 times negative 2, which is negative 4 plus 1, which is negative 3, and the absolute value of that is 3. 1 is not greater than 3, so the first portion will not be a part of our solution. Then we'll plug in a number from the middle, so we can use 0. So 0 plus 3 is 3. The absolute value of that is 3. Is greater than 2 times 0 is 0 plus 1 is 1. The absolute value of 1 is 1. 3 is greater than 1. That's true, so the middle portion will be a solution. Finally, we'll plug in something greater than 2, like 3. 3 plus 3 is 6. The absolute value of 6 is 6. 6 is greater than 3 times 2 is 6, plus 1 is 7. The absolute value of 7 is 7. 6 is greater than 7. That's not true, so this portion would not be a part of our solution. So our solution is these values here in the middle. So we have negative 4/3 is less than x is less than 2. For the second one, we'll have x minus 33 equals x squared plus 3, and x minus 33 equals negative x squared plus 3. We'll move everything to the left side. So we'll get negative x squared plus x minus 36 equals 0. So that's negative x squared minus x plus 36 equals 0. So x squared minus x plus 36 equals 0. This can't be factored, so we have to use a quadratic formula to get x equals negative b, which would become positive 1, plus or minus the square root of b squared, which is 1, minus 4 times 1 times 36 over 2 times 1, so over 2. So the inside of our square root here is going to be negative, so that would only give us imaginary solutions. So this first part has no solutions. Then for the second part, this becomes x minus 33 equals negative x squared minus 3. We'll move those to the left so that we can set it equal to 0. So we'll get x squared plus x minus 30 equals 0. This factors to x minus 5 times x plus 6 equals 0. So this means our solutions are x equals negative 6 and 5. Finally, we have 5 is less than or equal to the absolute value of x squared plus 1. So 5 is less than or equal to x squared plus 1. And negative 5 is greater than or equal to x squared plus 1. So 0 is less than or equal to x squared minus 4. So this can be factored. So 0 would be less than or equal to x plus 2, x minus 2. So x can be 2 or negative 2, and we'll have to figure out which direction that we're going to shade. But let's look at this second portion first. So for this one, we'd subtract 1 from each side, and you say negative 6 is less than or equal to x squared. If we take the square root of both sides, we have the square root of a negative number, so this part's going to have no solution. So we'll draw our number line with x at negative 2 and 2 and figure out where we need to shade. So if x is negative 3, then we'd have negative 3 squared, which is 9, plus 1 is 10. Absolute value of 10 is 10, which is greater than our 5. So we would shade this portion. In the middle, we could plug in 0. 0 squared plus 1 is 1. Absolute value of 1 is not greater than 5, so not the middle section. And then our last section will work. So we would have that x is less than negative 2 or equal to. And also, x is going to be greater than or equal to 2. So it would be this or this. So that's how you find solutions to modulus equations. So here we have our first IB practice question. It says on the same set of axes, draw f of x equals 4 over the absolute value of x minus 1 and g of x equals x plus 3. Label any x-intercepts, y-intercepts, and asymptotes. So we'll draw our x and y axis. So we have g of x equals x plus 3. So we'll go up 3, and it's x plus 3, so we'll have a y-intercept at 3 as well. And it's just going to be a linear function. So here's g of x. Then we have f of x is 4 over the absolute value of x minus 1. So if we plug in 0 to f of x, we'll get 4 over 0, absolute value of 0 minus 1, which is 4 over negative 1, but we take the absolute value of negative 1, so it's 4 over 1, which is 4. So at 0, we'll have 4 for f of x. If we plug in 1, then our denominator will be 0, so it'll be undefined. So at x equals 1, we'll have our vertical asymptote. And our horizontal asymptote will be when y equals 0 because it hasn't been shifted up or down at all. So we'll have a horizontal asymptote here. So vertical asymptote at x equals 1. horizontal asymptote at y equals 0. So since we have the absolute value on the bottom, both parts of our 1 over x function are going to be above our horizontal asymptote. So we'll have another point at 4 on the opposite side, and they're both going to be going like this. So this is our f of x. So the second part says find the exact solution where f of x equals g of x. So we want 4 over the absolute value of x minus 1 to equal x plus 3. So we'll start by multiplying both sides by the absolute value of x minus 1. So that'll cancel out the x minus 1 on the left side. And then we'll divide both sides by x plus 3. So we'll get 4 over x plus 3 equals the absolute value of x minus 1. So now we have the absolute value on one side of our equation. So we'll say 4 over x plus 3 equals x minus 1. And we can also say 4 over x plus 3 equals negative x minus 1. So for this first one, we'll leave our 4 over here and multiply both sides by x plus 3. So this will be 4 equals x squared plus 3x minus 3. So 4 equals x squared plus 2x minus 3. And then we'll move our 4 over to get 0 equals x squared plus 2x minus 7. To find our exact solutions to this, we'd use the quadratic formula. We'd have x equals negative b, which is 2, plus or minus the square root of b squared, so 2 squared, which is 4, minus 4 times a, which is 1, times c, which is negative 7, all over 2 times a, so 2 times 1. So this is negative 2 plus or minus the square root of 4 plus 28 over 2, which is negative 2 plus or minus the square root of 32 over 2. 32 is 16 times 2, so we can pull out a 4. So negative 2 plus or minus 4 square root 2 over 2. And then we can divide by 2 over 2, which will give us negative 1 plus or minus 2 root 2. So those are going to be our first solutions for what x equals. Now for the second part, we have 4 over x plus 3 equals negative x plus 1. We'll multiply both sides by x plus 3. So 4 equals negative x plus 1 times x plus 3. That gives us that 4 equals negative x squared minus 3x plus x plus 3. We'll subtract 4 from both sides and combine like terms. So this will give us that 0 equals negative x squared minus 2x minus 1. We can factor out a negative, so 0 equals x squared plus 2x plus 1, which can be factored to x plus 1 times x plus 1 equals 0, so x equals negative 1. So we have x equals negative 1 plus 2 root 2, and negative 1 minus 2 root 2. And those would be our solutions. So for this function right here, our x plus 3 has to be greater than 0. Otherwise, we'll get a negative value on the left side of our function, and an absolute value can't equal a negative number. So our x has to be greater than negative 3. And if we look at the results we got from it, our negative 1 plus 2 root 2 and our negative 1 minus 2 root 2, our negative 1 minus 2 root 2 is going to be less than negative 3. So that one can't be one of our solutions. So really, our only solutions are these first two ones here. So those are our final answers. So it's important to check all of the details to make sure that you have the problem correct. So here we have our second IB practice question, and for this one the calculator is allowed. It says solve the following inequality for x. the absolute value of 3x arc cosine of x is greater than 1. So you'll start by graphing your absolute value of 3x times the arc cosine of x, and you'll also graph y equals 1. So graph y equals this, and y equals this. So now you want to find your points of intersection. So when you find your points of intersection, you should have a point at negative 0.189, comma 1, 0.254, comma 1, and 0.937, comma 1. So our absolute value of 3x arc cosine of x starts when x is negative 1. So we'll draw our number line. We'll have negative 1, negative 0.189, 0.254, and 0.937. Our absolute value of 3x arc cosine of x is above our line y equals 1, between negative 1 and negative 0.189, and between 0.254 and 0.937. So negative 1 is less than x is less than negative 0.189, and 0.254 is less than x is less than 0.937. So x can be any of those first values or any of these second values. You can also write that in interval notation as negative 1, comma negative 0.189, union 0.254, comma 0.937. So there's your solution to that problem. In summary, our absolute value function takes all negative y values and makes them positive. Our absolute value of x makes our x values positive, but can still be shifted down to negative numbers. Our reciprocal function takes 1 divided by all the original outputs from f of x. Our function squared squares all the outputs of the original function. For our horizontal shifts and dilations, we can have a horizontal compression by a factor of 1 over a if the absolute value of a is greater than 1, a horizontal stretch by a factor of 1 over a if the absolute value of a is between 0 and 1. We'll have a horizontal translation left, b over a units, when b over a is positive, and a horizontal translation right, b over a units, when b over a is negative. For our solutions to modulus, you'll move the absolute value portion to one side of the equation and everything else to the other side, and then you'll take away the absolute value symbols and set one side of the equation equal to the other side of the equation and to negative 1 times the other side of the equation, and then solve. That's all for this video. Thank you for watching.